This is the next of our informed or heuristic search methods, which is A* search. If you remember, uniform cost search chose which node to expand next based on the total path length from the start to the current node, which we called G of n. Meanwhile, greedy search makes its choice based on a heuristic estimate of the path length from the current node to the goal, which we called H of n. Now, if we add these two values together, we get an estimate of the total path length from the start node through n and on to G. Since this is the thing we ultimately want to minimize, it makes sense to choose the next node for expansion based on the sum f of n equals g of n plus h of n, and this is exactly what A* search does. If we go back to the problem of finding the shortest path from Arad to Bucharest using this map of Romania, we see that the straight line distance from Sibiu to Bucharest is 253, which, when added to the path length from Arad of 140, gives a total of 393. This value is smaller than 449 for Zarind or 447 for Timisoara, and so Sibiu is chosen as the next node for expansion. Remember, greedy search chose Fagaras next because it's closer to the goal, but A* search prefers Rymnicu-Vilcea because the straight line distance of 193 plus the path length from the start node of 220 gives a total of 413, which is slightly smaller than Fagaras at 417. This generates Pitești, which becomes the preferred node at 415. Because Bucharest is the goal, its estimated distance must be 0, so the value of 418 is the actual path length from the start node to Bucharest, but we can't stop the algorithm yet because our estimate for Fagaras is a little bit shorter at 417. So based on this information, it's still possible that there might be a shorter path to Bucharest going through Fagaras. So we have to expand Fagaras just to make sure that there isn't a shorter path. But then we find out that the path through Fagaras is actually somewhat longer at 450, and in fact, all of these estimates in black are larger than 418. So at this point, the algorithm can stop, and we are certain that there is no shorter path to Bucharest. But notice we're relying on the fact that these straight line distances are always the same or shorter than the true path length. That's why we know that all of these numbers are actually underestimates, and so there couldn't possibly be a shorter path. A distance estimate with this property of always underestimating the true path length is called an admissible heuristic. Now I'm going to show you a formal proof that A* search is guaranteed to find the shortest path so long as the heuristic is admissible. Now remember, we have a set of nodes that have been already expanded, and then we have a set of nodes which have been generated but not yet expanded. And the algorithm terminates at the point where the next node scheduled for expansion is actually a goal node, G, and remember that the nodes are expanded according to this function f, which is a sum of G and H. Since G is a goal node and H is an underestimate of the distance from G to the goal, that means H of G must be 0. Now let's consider any other path from S to a goal. It could be the same goal G, or it could be a different goal G prime. In either case, if we follow this path starting from S, at first we go through nodes which have already been expanded, but eventually we cross this boundary and we find the first node along this path which has been generated but not yet expanded. Let's call that node N. It doesn't really matter whether it's G or G prime, but for simplicity, let's assume it's G prime. Now, because N was generated, it would have been a candidate for expansion, but somehow G got expanded first. So that means f of G must be less than or equal to f of n. But f of n is equal to the path length g of n plus the heuristic h of n. And because h is admissible, that means h of n must be less than or equal to the true path length from n to g prime, which we call h star of n. And g of n plus h of n must be less than or equal to g of n plus h star of n, which is the true path length all the way from s through n to g prime. This proves that the path we originally found to G must be shorter than any other path to a goal, and therefore the algorithm is optimal. A-star search is a fantastic algorithm because instead of searching equally in all directions, it instead concentrates the search on those nodes which are most likely to lie along the shortest path to the goal. So it uses a lot less memory than uniform cost search. One final point though, on some very large problems, A-star search might still run out of memory. And for those problems, we switch to an alternative version called Iterative Deepening A-star search, which does a series of depth-first searches, but each one is limited to a certain maximum value of this function f equals g plus h. And using that variant, we can solve even large problems like Rubik's Cube, if we have a clever enough heuristic.